Hello everyone, I hope you are all well. My name is Adel and today I want to present our paper titled Modeling and Model Transformation as a Service towards an Agile Approach to Model-Driven Development. First of all, I want to thank the chair and the program committee of the LASD Conference 2022 for this opportunity. I would also like to acknowledge invaluable feedbacks from our reviewers that helped us to improve the paper. Agile methods are widely used in the software industry, although they strive to expedite software development and delivery as much as possible. They also pay special attention to enhancing flexibility in order to respond to change in a timely manner. In model-driven development, models play the primary role throughout the process of software development. One of the motivations for using this approach is to automatically generate the code from the models of the system by executing a chain of model-to-model transformations and model-to-text transformation. It might seem that agile development and model-driven development are poles apart. Agile methods are lightweight, fast, responsive, and adaptable, while model-driven approaches are heavyweight and require early investment in modeling. Agile methods focus more on the process and methodological aspects of software development, while model-driven approaches rely on architectural aspects and separation of concerns. Nevertheless, it has been observed that by combining these two approaches, we can take advantage of the strengths of both and cover some of their weaknesses. There are several reasons for integrating agile methods and model-driven approaches, including improving agility and minimizing unnecessary tasks, increasing collaboration, enhancing requirements analysis, reducing risk by receiving early feedbacks, accelerating response to change, increasing the level of automation, managing complexity, building the models in an iterative incremental fashion, and a better understanding of the problem domain. A prerequisite for integrating Agile and MDD methods into Agile MDD process is to be familiar with the strengths and weaknesses of these two areas. Agile methods have come a long way as to their support for scalability, but scalability is still a serious problem, especially in large and complex projects involving distributed teams. Over-reliance on face-to-face conversation as the sole means for conveying information, and avoidance of modeling at all costs can be detrimental to scalability. This poses a challenge to coordination and communication in distributed teams. Models as a common language and basis facilitate communication and interaction between different teams. The strong motivation for using MDD are the continuous evolution of software technologies and the ability of this approach to generate the code from models automatically. Model-driven architecture with three modeling levels of computation independent model or CIM, platform independent model or PIM, and platform-specific model or PSM facilitates software evolution by separating the problem domain from the solution domain and establishing a mapping between them. If the problem domain models change, these modifications are propagated to solution domain models through the model transformations. But if the solution domain changes, for example, by adopting a new technology or platform, we only need to modify the mapping and the changes will not be propagated to the problem domain models. So, integrating Agile and MDD approaches improve the scalability and facilitate software evolution and maintenance in Agile methods to some extent. But on the other hand, it poses challenges from MDD perspective. Model-driven methodologies have a heavyweight processes that have a negative effect on agility. Modeling large and complex systems in an iterative, incremental fashion, and collaboration among teammates during modeling activities in large distributed teams are other challenges of MDD. So, the scalability of MDD approaches in terms of model size and the number of modelers involved in the modeling process should be improved. Moreover, we need to adhere to Agile values and use best practices in Agile modeling. MDD requires early planning, investment, and design. This early investment can add value when the assets produced during these steps can be reused frequently. Therefore, production of reusable artifacts and responding to changes by demand is another challenge of MDD. Accordingly, we propose a new agile approach to MDD by using service-oriented concepts. The purpose of this approach is to facilitate participation and collaboration in the modeling process and to improve scalability in terms of model size and the number of modelers involved in the modeling process. To this aim, we introduced the idea of multi-level modeling as a service and model transformation as a service and propose a new model-driven architecture. Software systems are complex in nature and many are distributed as well. Different teams can be involved in the system development process, but the members of these teams are not necessarily co-located. The key question is how to manage the modeling complexity of the problem domain and improve collaboration in the modeling process. In MDD, the meta model is first defined by identifying the domain concepts, which are then instantiated to yield the model elements. Accordingly, the model must conform to the syntactic rules and constraints defined in the meta model. In this paper, we use model decomposition for managing complexity in modeling processes and propose three approaches based on the meta level to which decomposition is applied. In the first approach, a meta model is defined for the entire domain, and the problem domain is described in the form of a single model. This approach is suitable for describing simple problems, but faces serious challenges for large and complex systems. From a scalability point of view, we encounter a large and complex meta model that contains all the domain concepts and syntactic rules. Validation and maintenance are difficult. It is not possible to get early feedback from the user. If the meta model is modified, these changes should be reflected in a large and complex model. This approach lacks agility and makes iterative incremental modeling impossible. From the perspective of cooperation and collaborative modeling, this approach also faces various issues. The second approach uses a single meta model to define the concepts and rules of domain-specific modeling language, but manages model complexity by domain decomposition, breaking up the problem domain model into multiple partial models. The partial models describe different parts of the problem domain, and an overall model is obtained by integrating these partial models. In this approach, the same language is used for describing different contexts of the problem domain. Each context can have its own model and model repository. So, in asynchronous collaborative modeling, it is not necessary to load all the specifications of the problem domain. Each team can load, describe, and modify the specification of the areas assigned to it as modeling tasks. However, the operational cost of maintaining multiple repositories and interdependencies between different contexts and integrating them is the price that should be paid for reducing complexity and improving scalability and collaboration. In the third approach, breaking up the problem domain takes place at both metamodel and model levels. Therefore, in order to describe the same aspect in different contexts of the problem, the context-specific metamodel of each part is first defined, and the problem domain is then described from that perspective with the help of models that conform to context-specific aspect-related metamodels. In this approach, separation of concerns helps manage complexity. Also, instead of defining a large and complex metamodel that considers all context-related concerns, several lightweight and context-specific metamodels are developed. This improves the reusability and maintainability of the metamodel and related models. If one metamodel changes, we only need to maintain the compatibility of its corresponding models. It also allows for gradual and evolutionary modeling and contribute to the agility of the modeling process. By assigning the tasks related to the modeling and meta-modeling of each context to a team, different teams can concurrently collaborate in the modeling process, thus enhancing collaborative modeling. In this approach, the overall view of the problem domain from a specific perspective is generated by integrating the partial models of different contexts of the problem domain, and model transformation play a key role in this regard. All of these benefits make the third approach a wise choice for Agile MDD. The complexity of integration is the cost that should be paid to improve cooperation, scalability, and mutual independence of teams. Identifying and distinguishing the different contexts of the problem domain can be challenging. If the logical boundaries between the different contexts of the problem are not well identified, the integration will become difficult. A coarse-grained metamodel can be decomposed by considering the following goals: increase the cohesion of fine-grained metamodels, form autonomous teams, and improve participation and cooperation in the modeling process. The bounded context pattern can be used as a guideline and mechanism to decompose metamodels with respect to these goals. The independence of teams in developing different parts of the software system may be the basis for deciding how to break up the metamodel. Reducing inter-team dependencies allows different teams to work in parallel. This improves agility and cooperation in modeling activities. As a rule of thumb, the bounded context pattern can be used as a guideline and a starting point for decomposing a coarse-grained metamodel. Later on, two context-specific metamodels can be merged and assigned to a single team according to other concerns and criteria, including reducing inter-team dependencies, saving on integration and operational costs, and reducing the collaboration costs resulting from the geographical distribution of the teams. Traditional modeling approaches Model the relationships among the elements in a tightly coupled manner. Suppose that there are two classes called order and customer in a model, which are identified by two members of the team. There is an association relationship between order and customer, but the association relationship between them cannot be defined before defining the classes themselves. This will tie the design steps of the two team members together because modeling the relationship between the two elements is highly dependent on the presence of both at the moment of relationship definition. Designers usually model the system from the perspective of an outside observer, while the problem space can be viewed from the perspective of each of its constituent elements. In the previous example, the order describes the situation from its perspective as being related to the customer, but the presence or absence of the customer element at the moment of describing this situation does not change the reality of the problem. This is only a technical concern to consistently define the model. Therefore, relationships should be modeled asynchronously and loosely. In this approach, instead of modeling the problem domain only from the designer's point of view, we describe it from the perspective of each concept in the different contexts that make up the domain. For example, if order has a unidirectional relationship with customer, from order's point of view, there is a specific relationship with a concept called customer. But customer does not need to know anything about this relationship in the customer management context. In other words, the customer does not even know that a concept called order is present in the problem domain because describing the problem domain from a customer management perspective does not require any such knowledge. In addition, order does not need to know about all the customer-related attributes defined in the customer management context, for example, date of birth. The loose connection between order and customer can be realized by using an event-driven architecture. Order states that it has a specific relationship with customer. From an event-driven point of view, it can be interpreted that order is interested in being informed when customer is modeled, or if it already exists in the scope of the problem domain. When customer is described in the problem domain, it announces the fact of being existent in the form of a published event. Using the publisher-subscriber pattern, it will be possible to model the relationships between two concepts in a loose manner. This approach allows for asynchronous modeling, which improves the participation and collaboration of team members in the modeling process. The cost of this approach is that the model may sometimes be inconsistent, but this type of inconsistency can be resolved by completing the modeling process. In the long run, it seems that improving flexibility, enhancing participation and collaboration, reducing dependency, and increasing scalability outweigh the temporary inconsistency of the domain model. Problem domain decomposition and describing it from the perspective of each domain concept allows complexity management at fine-grained levels. However, it is the modeler's responsibility to provide a macro view through the integration of these micro views. In this regard, we have introduced the idea of concept as a service, in which the problem domain is described in terms of different domain concepts, each concept being embodied in the form of a self-contained service. This service makes it possible to define a concept from three perspectives: structural, functional, and behavioral. It also provides essential functionalities required to query the structural, functional, and behavioral specifications of a concept. A simplified version of the proposed abstract syntax for describing each domain concept from these perspectives is shown in this figure. Since each domain concept is realized in the form of a self-contained service, it will be possible to provide a high-level view of the problem domain through the integration of these services. One of the problems with conventional modeling approaches is that existing facilities for defining meta-models cannot be used at the model level as well. So if we need a new type, we have to define it explicitly at the meta-model level. To overcome this drawback, the notion of multi-level modeling was proposed, which allows in-depth definition of a language in more than two levels. Several techniques such as potency-based multi-level modeling and orthogonal classification architectures have been proposed to extend the standard modeling approach. Based on the notion of concept as a service, we propose the idea of multi-level modeling as a service and transformation as a service that extends the OCA technique and describes the problem domain and solution domain from three dimensions: ontological, linguistic, and relational. In this figure, an example of multi-level modeling from ontological and linguistic dimensions is shown. The third dimension, or relational dimension, is embodied in our proposed model-driven architecture. This dimension focuses on the relationship between two elements of two models in two different abstract layers. By analyzing the problem domain and exploring the subdomains and concepts, domain concepts are first constructed. Then, by creating new instances of the domain concept, domain objects are created that actually form the domain model. A domain object has two facets. On the one hand, it is an instance of its ontological upper-level domain concept. For example, film is an instance of product. On the other hand, it can be considered as a template for instantiation of its ontological lower level and thus play the role of a domain concept for the level below. For example, film is a type for Star Wars. MDA is the main architecture adopted in MDD. Traditional MDA follows a layered structure, while our proposed model-driven architecture has an onion structure. In our proposed MDA, each layer provides access to its model elements and their descriptions to its higher layer through services corresponding to these elements. To promote the participation and cooperation of domain experts and the development team in the modeling process, a common language is required. To this aim, we have introduced a method called CRAC, standing for Concept, Responsibilities, Asynchronous Collaboration, which aims to explore the problem space and reach a common language between domain experts and development team. In this method, we first identify the concepts of the problem domain. Each concept plays a role in the problem space, and other concepts in this context have an expectation of it. that can be interpreted and expressed in terms of its responsibilities. A concept's responsibilities can be accomplished or failed, and it is possible to deduce a set of facts or events that explain this situation. Concepts can also be interested in a set of facts and events in order to fulfill their responsibilities. They can also react to an event when being informed about a fact. This information is described in the form of a model consisting of these elements: concepts, commands that are executed by a concept, events that are published as a result of command executions, events that a concept is interested to know about it, and commands that are executed in reaction to the event of interest. For each concept, these four pieces of information can be inserted on both sides of a crack card. In order to improve collaboration between domain experts and the development team, a Google spreadsheet can be used to describe and access this information simultaneously. This figure shows the analysis model of an online food ordering system produced by the crack method. The system must be able to receive orders. If an order is submitted successfully, the order created event will be published. Restaurant is interested in order created events. When this event occurs, it asks the kitchen to issue a ticket for the order. The kitchen can accept this order and issue a receipt or not issue it due to running out of food. The identity of the owner of the order should be verified when the order is created. Customer identity may be approved or rejected. When the customer is verified and the order receipt is issued by the restaurant, the customer's credit card should be checked. At this stage, the card may be approved or rejected. Order is interested in these events to confirm or reject the order. If the credit card authorized event occurs, order invokes the approve order command, and the order approved event is published as a result. Otherwise, it invokes reject order, and order rejected event is published. Similarly, restaurant needs to know if the order is approved or not. If the order is approved, restaurant approves the issued receipt by invoking the approve ticket command, which will result in the publication of the ticket approved event. But if the order is rejected, restaurant rejects the ticket by invoking the reject ticket command, and ticket rejected will be published as a result. Other requirements of the online food delivery system can be analyzed and modeled in the same fashion. The crack analysis model is produced. It is transformed into concept-based models which constitute the CIM level models and are represented in the form of self-contained and self-descriptive services at the CIM level. Next, we need to describe design details and solution concerns. However, these specifications don't directly apply to CIM level models, but are rather expressed using the specific language of the PIM layer. If the partial models described at the PIM level require the specification of CIM level concepts, they refer to the concept described at the CIM level without the need to redefine this information at the PIM level. Integrating design details at the PIM level with the specification of CIM level concepts is done automatically using the built-in or user-defined model transformation services. The third dimension or relational dimension of our multi-level modeling approach is shown in more detail in the right-hand side figure. The relation dimension includes PIM to CIM relation, PSM to PIM relation, and code to PSM relation. In current model-driven practices that is shown in the left-hand side figure, CIM level model elements are tagged to provide design details that are not presented in the CIM level models. And model transformations use these annotations to conduct transformation steps and produce PIM level models. This approach contaminates the analyzer's model with design concerns and reduces its readability and expressiveness. If design decisions change, we will need to re-annotate the analyzer's model. While in our proposed approach, CIM models remain intact and are not corrupted by solution domain issues. Rather, these details are described separately using PIM level domain concepts and are automatically combined with CIM models to generate PIM models using the model transformation services. The idea of model transformation as a service is based on an event-driven architecture that allows reactive model transformations. In other words, model transformations can be performed not only at the user's request, but also in response to the creation or modification of domain objects. One of the main components of a model transformation is the source model. When a model transformation service is defined, it declares that it is interested in receiving events related to the domain objects that correspond to its source model. By creating or modifying a domain object, a relevant event is published and delivered to the model transformation services that subscribe to the event. Upon receiving this event, the model transformation service initiates the process of deserializing the event and extracting the domain object identifier, retrieving domain object specification from corresponding services, performing transformation steps, and creating one or more target domain objects conforming to the destination model. Our preliminary analysis shows that the idea of modeling and model transformation as a service is in line with the values, principles, and best practices of Agile modeling, describing the problem domain in terms of concepts and modeling the relationships among these concepts in a loose manner facilitate collaboration throughout the modeling process and improves scalability in terms of the number of modelers involved. It allows for iterative incremental modeling due to loosely modeled relationships and the proposed model-driven architecture. It can also enhance agility by increasing the level of automation in code generation. The proposed crack method fosters mutual and shared understanding between domain experts and the development team, and facilitate collaboration and user involvement in the modeling process at the CIM level. The tool used for modeling at this level is simple and understandable to non-technical users. In our proposed approach, production of high-level models from lower-level models enhance the reusability of modeling artifacts. At each level of modeling, one can focus only on specific concerns of that level. Realizing the idea of model transformation as a service in the form of an event-driven architecture makes it possible to automatically propagate the change occurring in lower level models to higher level ones. Moreover, by integrating and composing fine-grained model transformation services, it is possible to execute reactive model transformations concurrently or as chains. Applying a service-oriented approach in modeling and model transformation allows for the use of different patterns and architecture style such as microservice architecture. Examining the two areas of service orientation and modeling and establishing a semantic correspondence between the challenges of these two fields will be one of our future research activities. This will help us apply the patterns and techniques used in the service-oriented paradigm to solve the problems and challenges of the model-driven development. Providing a model-driven development platform by using the service-oriented approach has also been planned as a future activity. The goal of MDD platform would be to support all functionalities required to fully realize the ideas of modeling and model transformation as a service. Thank you for your attention and watching this video. Please feel free to contact me if you need any further information. Have a nice day and stay safe.